Harmonic analysis of a triangular waveform by using piecewise. This is under harmonic analysis of non-sinusoidal waveform. So in this, by taking triangular waveform, so we have to find total harmonic distortion (THD) by using piecewise. So from piecewise, take from piecewise library, take V pulse and place on drawing sheet. Similarly, take one resistor of resistance 100 ohms and also take one probe, voltage probe. So it is so voltage marker connected by this, and also label is called 1 and this ground label is called 0. Okay, so like this connect this, and this V pulse inside of the V pulse DC is equal to 0. Similarly, AC is equal to 0 and V1 is equal to 0 and V2 is equal to 100. That means waveform starts from 0 to 100. Okay, and delay time 0, TD is equal to 0 and rise time is equal 1 milliseconds. Rise time is equal to 1 milliseconds and fall time TF is equal to 1 milliseconds. Rise time and fall time more compared to pulse width, and also pulse repetition is 2 times of rise time or fall time. Then we will get a triangular waveform, exactly triangular waveform. Okay, that's why rise time TR rise time is 1 milliseconds and fall time is 1 milliseconds, but pulse width is very less. Okay, so that's why pulse width is in 1 nanoseconds. That pulse repetition PER, pulse repetition is nothing but 2 times of rise time or fall time. Then we will get exactly triangular waveform. And then after this adjusting this settings of V pulse, then go for analysis, setup, enable transient, this box, enable, and then transient, go to transients. Print step is equal to 0. For example, maybe 2 milliseconds. Print step is equal to 2 milliseconds and final time is called 10 milliseconds. And similarly, enable Fourier series, enable Fourier. Center frequency is equal to 500 edges. Take 500 edges. And the number of harmonics called 9. Okay. And output varies called V of 1. Okay. So this probe is connected. Here the probe is connected across pulse and resistor. No? That is called 1. That's why we have to write V of 1. Clear? So number of harmonics called 9. Center frequency 500 Hz and enable 4. Then OK and close. So after that simulate. Okay, and then new pop-up appear like this. This is called triangular waveform. Okay, triangular waveform. So like this triangular waveform is generated. So this is called 0 volts to 100 volts. V1 is equal to 0, V2 is equal to 100. That's why it's the maximum peak is called 100. And final time is called 10 milliseconds. That's why the graph will be displayed up to 10 milliseconds. Okay, and rise time is called 1 milliseconds. So this is called rise time. And fall time is called 1 milliseconds. Rise time and fall time are 1 milliseconds. Pulse width is equal to very less time. No? That's why 1 nanosecond. Nanoseconds means approximately 0. That's why this is called pulse width. Pulse width is not up here. Compared to pulse width, the rise time and fall time is more 1 millisecond and 1 millisecond. And pulse repetition is called 2 milliseconds. Here on also again pulse is repeat. After 2 milliseconds, the pulse is repeat. 4 minus 2, 2 milliseconds. After 2 milliseconds, the pulse is repeat. So this is called generation of triangular waveform. After this generation of triangular waveform, press this icon FFT. Okay, Fourier FFT. Press this icon and then spectrum, that is called harmonic spectrum, display like this. Okay, in this harmonic spectrum, first this is called a fundamental. So enable toggle cursor and find the corresponding voltage. So here approximately So place like this, enable toggle cursor, and here mark label. So 497 means approximately 500 edges key, 500 edges. For 500 edges, this voltage is called 39 point, frequency is called 39. 500 edges, fundamental frequency here 500 edges. So that's why. So for 500 edges, 39.54 is the voltage. So like this we have to find. And similarly here also, this also mark level. So 1.51 kilohertz, 1.5. Okay, 1.5 kilohertz. The voltage is called 3.8840. 3.8840. So 1.5 kilohertz. And then similarly here, the voltage is called 2.47 kilohertz. So approximately 2.5 kilohertz, and this voltage is called 1.2153 voltage. And similarly, this is also okay, mark label. And then this display, so different types of harmonics. Okay, after getting this harmonics, then go to view and output file, simulate output file, and then here number of harmonics called 9 harmonics. Here the number of harmonics are called 9. These are the number of harmonics, total harmonic distortion. Okay, here total harmonic distortion, that is equal to 1.2059 into 10 to the power of 1%. So that means 12%. The total harmonic distortion approximately equal to 12%. So, how to find the total harmonic distortion means by using one formula that is called under root of V3 square plus V5 square plus V7 square plus V9 square. Like this, different types of harmonic voltages, square of the harmonic voltages by fundamental. So here in this waveform, this is called 500 is called 500 this is called fundamental. Corresponding the fundamental voltage is called 39.540, and this is called next harmonic voltage 1.51 is called this harmonic voltage is corresponding this voltage is called 3.84, and here corresponding 2.5, this is the called 1.32. So like this, different types of harmonics the voltage generated. Then how to find a THD for these different types of harmonics means by using that formula THD, square of the harmonic voltage is d by fundamental under root. Okay, this is called 40 is called fundamental harmonic voltage. Fundamental harmonic voltage for 500 edges. So this is called for 500 edges. That is called fundamental frequency. This is the voltage generated. And then next harmonic voltage 1.5 kilohertz. This is called 4.5229 voltage. That's why so square of this voltage, and 1.399 the square of this voltage, and plus 0.714 square, there will be 40 square. So then 119.69 into 10 to the power minus 3 is nothing but 0.119. That is nothing but in the form of percentage 11.9%. That is called THD is equal to 11.9%. That means approximately 12%. Okay. So like this we have to calculate theoretically by using formula total harmonic distortion THD is equal to under of uh, harmonic voltages, square of the harmonic voltages by fundamental fundamental voltage square. Okay, in this way we have to find the total harmonic distortion. So this is about total harmonic distortion THD, to find the total harmonic distortion of a triangular waveform. So by pressing the FFT, the harmonic voltages are displayed like this, and harmonic spectrum can be displayed like this. After this, by pressing this, go to view and simulate output file, and then in this output file, these are the number of harmonic voltages. For total harmonic distortion is equal to 1.2, so that is called approximately 12%. So theoretically calculated and this practically executed values are both are same. So this is about total harmonic distortion of a triangular waveform or non-sinusoidal waveform.